All right. Welcome back, everybody. Today's Tuesday. Everybody's online day. Okay. So let's just get started with updates. Okay. So this is a new update announced yesterday. So you already know. So tomorrow is a Wednesday, June 16th. We are going to have a quiz of section 3A toward the end of the lecture class in class lecture on Wednesday tomorrow. And also tomorrow 9 a.m. you're going to submit homework assignments of section 3B, which is a trust programs. I hope you're working on it. And then if you have any question, I'll be happy to spend some time going over your questions. Okay. The homework of 3B is due tomorrow 9 a.m. And also Thursday 17th, you're going to take the quiz of 3B. Okay, again, the last 10-15 minutes of the in-class lecture. Since this is trust problem, I'll give you a little bit more time, not 15, probably 20-ish minutes. I haven't decided yet, but I'm going to probably give you more time to do trust problem. Do you have any question about updates? Any question? If you understood, please react or something. Good. Appreciate. Ab Abiyad, please react. Okay. All right, good. So today we are going to get into Unit 3C. Okay. Internal loadings and frictions. Internal loading we already sort of introduced when we do thrust analysis method of sections. Do you remember? So in order to expose internal loading, expose. Am I correct? I don't know. Internal loading. By virtual cut. Okay. We already did it for thrust analysis. This is method of sections, correct? So we are going to actually apply method of sections or virtual cut for a member. May not necessarily be like a truss, which is 2/4 member. So if you cut through member, you're going to expose actually three unknowns, three unknown internal loadings. If it's 3D, oh no, if it's 2D. If it's a 3D problem, it's going to be 6 unknown loadings you're going to expose. And then you're going to apply equations of equilibrium to find out those unknown internal loadings. That's what we are going to do here. And then after that, this is actually very, very important subject. We are going to try to draw shear and moment diagrams. This is going to reappear in solid mechanics, ES202, solid mechanics. This is going to be very important fundamental steps to analyze materials inside of the body in solid mechanics. So you're going to actually start doing virtual cut, exposed shear, and moment within a given structure, typically a beam. And then you're going to draw a diagram, how the shear and moment internal loadings, okay, those are internal loadings, how do they distribute within a beam? Well, what is the beam? Maybe this could be a beam. So suppose if you design and build this kind of structure, how much internal loading is developed at, let's say, right here, or right here, or here? How much internal shear and moment is developed within this structure? You can, of course, find out, or even you can draw a diagram for that. Okay, that's the important first step to solve materials internal shear stress, materials internal bending moments, and based on bending moments, you're going to develop normal stresses inside or shear stresses inside because of the shear stress, shear loading. Do you choose the proper material and proper design of the size of cross section? You can find out all of those things by starting from this. Okay, so this is very important fundamental knowledge. If you don't understand this, people usually have very difficult time surviving in this class. Okay, so stay focused. And then we're going to finish up this section with dry friction and wedges, something called static friction forces. Okay, let's move on. So internal loadings we already looked at. Remember, we had a very good, very healthy discussions when we tried to solve truss. Now truss is actually very simple two-force member. Do you remember this? So here's a truss, something like this. Then method of sections basically allows you to cut just about anything, or maybe you can cut two locations of this particular member. You can pick up this member and at each cut section you are going to introduce internal loading, in which this case for the truss it's a two-force member, so force is always single force in the direction or axis of each member. This is two-force member, so either in this case tensile or could be compressive. That's the only thing you can decide based on the method of sections. However, if you're talking about more advanced structures such as this is a beam, by the way, this beam can support perpendicular forces as well as force in the same direction similar to this member, or you can even apply moment at certain location. You can take actually distributed loading on this member. You can take a variety of loadings, external loadings. So if you cut through a certain segment, typically the perpendicular to the main axis of this beam, you're going to introduce, if it's 2D, three unknowns. Okay. What kind of unknowns? Well, three type. One is a shear force. This is a component perpendicular to cut surface. Okay. This is a shear. And the other one is normal force. This is component perpendicular to, not parallel to, sorry, parallel to cut surface. So obviously those two are not the same type of forces. Now in truss, we only talked about this normal force. So I should use the same color. Sorry about that. So in case of truss, we only see this normal force. Okay. Now the other type is something called moment. Now we have two different kinds of moment. You have to be very careful about that. Just like we have to have, we are going to have two different kind of forces. One is perpendicular to cut surface. one is parallel to the cut surface. We have two different kind of forces as well. We have two different kind of moments. Now, let's just take a look at the 3D. So this is 2D, okay? 2D member. Three internal loadings, okay? Now, if you're talking about 3D member, now this now becomes 6. Okay. So obviously you have a force in 3 directions. Force in y direction is called normal force. Force in y direction is the force which is essentially, wait a minute, I'm saying completely wrong thing, isn't it? Let me just erase this, erase that. Sorry. This is, by the way, parallel to the cut surface. That's called shear, sorry. Perpendicular to the cut surface, that's called normal force. That's right. So this is completely perpendicular to the cut surface. This is a cut surface. You are going to expose this cross section by doing virtual cut of a member. Now, the force perpendicular to this cut surface is called normal force. Okay. Again, perpendicular to the cut surface. Okay. And you have two different type of forces, BZ and BX. Those are essentially parallel, or in the direction parallel to the surface. It's called the shear force. Okay. So you have two different shear forces, shear in Z direction and shear in X direction, and then one force which is a normal, which is completely perpendicular to the surface, which is normal force, which is Y direction component of the force. So you have three different forces. Two of them are shear, one is normal. Okay, sorry about that. And then you have, again, two different type of moments. Now, the moment here on 2D is something called bending moment. Moment that actually try to bend this thing, either this way or that way. You're trying to bend this material. It's called bending moment. Okay. So this is the bending moment. Moment in x-axis direction is bending moment. This is the bending moment trying to bend the material this way. And the other moment is a bending moment in z direction, in which you're trying to bend this way, that way, this way, that way, and then this way, that way, this way. So two different kind of bending moment, obviously. And then the other moment is something called torsion moment. Okay, interesting word. Torsion moment. This is, by the way, torque. Torsion is you're going to try to twist this whole thing. Torsional. Okay, this is called torque. Okay, so two different kinds of moment: torsional moment and bending moments. Two different kinds of forces: normal force and shear force. Okay, so that's the perspective of a three-dimensional material. Total six internal loadings. Now, if you're looking at only, in this case, you're only looking at typically XY plane. So this is a bending moment on XY plane. That is moment in Z direction, isn't it? Okay, if it's a right-hand coordinate XY plane, this is moment in Z direction, trying to bend this whole thing onto the 2D plane. Okay. Any questions so far? Please don't hesitate, all right? If you don't understand what I'm talking about, please stop me and unmute your microphone. You can say anything you want anytime, okay? So if it's okay so far, please react. Okay, so far, everybody? Okay, good, good, good. Appreciate that. You're with me. All right. So next page. So this is something we already did, okay, to do a truss analysis. Now, this is no longer truss. Too bad. Truss is a two-force member, so if you cut through each member, at each cut section, you're going to introduce only one force because that's two-force member, okay? The only force you're going to expose is essentially normal force, okay? If it's truss, because it's two-force member. Now, you're dealing with now machines and frames and more general type of structures. Every time when you introduce your cut, you're going to introduce three unknowns. In other words, normal force, shear force, bending moment at each cut segment. So all of a sudden, you introduce three unknowns at each cut section, okay? So obviously, it is going to make it more complicated to solve the problem, okay? So you have to understand how many maximum unknowns you can handle. Obviously, you need to be aware. This is completely 2D problem, so the maximum number of equations you can have is 3. Summation of force in x and y, and the moment taken at any location set equal to 0. That's the only equations you can have. So suppose if you introduce like 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 unknowns. You can never solve those 9 unknowns. Of course, you only have 3 equations available. So you have to disassemble, 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 create free body diagram, and free body diagram, and free body diagram. Apply 3 equations each for each 3 free body diagrams you construct. And realizing if you assemble here, point B, you're going to have an equal and opposite force. So that cancel each other. So solution is going to be more lengthy. It's not difficult, but very redundant. Okay, lengthy solution. So that's one thing you have to realize. Okay, so next page, let's just take a look at the example problem, easy one to begin with. Okay. Class example 391. Determine the internal normal force, shear force, and the bending moment in the beam at point C and D. Assume the support at B is a roller. That means single y direction support reaction force. Point C is located just to the right of the 8 kip load. Just to the right. Okay. So interesting program statement. Let's just take a look. Okay, so I'm going to draw a free body diagram. Let me just zoom in a little bit. Okay. So free body diagram of the entire thing to begin with, because it looks like this is a 2 support reactions, this is 1 support reaction. By taking the entire free body diagram, applying 3 equations of equilibrium, you can determine the support reaction forces A and B, looks like. So let's just begin with free body diagram of the entire thing. This is a beam, okay? So let's just draw it. So this is a beam. I'm going to disassemble pin at A. And then this is the roller at the B. By disassembling it, I'm going to introduce unknown forces. So this is the support reaction at the pin A in Y direction, AY. And support reaction at the pin A in X direction, AX. And then here is a support reaction at the roller, BY. So 3 unknowns you introduce. Then external loading, 8 kip. What the heck is kip? Anybody? What is kip? Do you know?
Kilopounds.
Kilopounds. That's a terrible unit, isn't it? 8,000 pounds. Okay, 8,000 pounds. I don't know who created it, but it's a terrible unit. Okay. And this is C. Okay. This is D. And then dimension 8 feet, 8 feet, 8 feet. I'm not going to put the dimensions. I don't want to crowd up my figure. And also, don't forget, there's a moment applied. This is externally applied moment at, looks like point B. Okay, so this is 40 kip foot. This is a 40, yeah, 40 kip foot. I'm going to use kip anyways. Okay, so let me just change it a little bit. I'm going to use kip in my computation. Okay. All right. So this is a free body diagram. All right. I'm going to apply simple one. Summation of forces in x direction. Set equal to 0. This actually gives you AX is the only force in x direction, so well, AX is 0. All right, this is easy. And then next is, well, I'm going to apply moment. Let's say this is a positive moment direction. Summation of the moment, let's say take it at the location A. Let's just set equal to 0 because this is going to eliminate AXAY as a moment contribution. So this is going to give you, okay, BY is going to create positive moment. BY multiplied by distance from here to here is 24 feet, which is positive. And 8 kip create negative moment. Distance is 8 feet. And don't forget, externally applied couple moment. This is a 40 positive. 40 kip foot. If you add them up, must be equal to 0. This is going to give you BY. BY is equal to 1 kip. Okay. And summation of the force in y direction. Set equal to 0. AY is a positive direction. This is a negative 8 kip. And BY, we found 1 kip positive. This is going to give you AY. AY is 7 kip. Okay. Okay, so far. So now we found all of those, excuse me, support reactions. We know this is 0. All right. So the next step is, since you are looking at internal normal force, shear force, and the bending moment in the beam at point C and point D. So what you need to do is you're going to virtually cut through the point C and virtually cut through point D. So let's just take a look at point C. So what are you going to do? You're going to basically cut through point C. Virtual cut. Now, important thing is the program basically says that the point C is located just to the right of the 8 kip road. So you have to include this 8 kip loading as you cut. So this is after you cut, you can either pick up this one or that one, construct the free body diagram again as a cut member. So this is point C cut. So this is cut section point C. So I'm going to call this here point C. And then since this point is to the right of the 8 kip loading, so 8 kip is still appearing here. Okay. And this is the joint A, which you determined AY, which is 7 kip. Okay. Since you cut through point C, you are going to introduce 3 unknowns right here. One is something called normal force N at C, location C, and also internal shear force BC, and then internal bending moment MC. So 3 unknowns shows up. Those are the internal loading you want to find out by applying, once again, 3 equations of equilibrium. So let's just do that. Summation of the force.
Professor?
Go ahead.
So with the direction, it will be like we did in the trusses, like if you get a negative number, so it's the other direction of moment, or...
Important thing, you're talking about sign convention. Okay.
Yeah,
sign
like
convention.
with the
That's right.
moment and...
Let's just talk about sign convention. Just take a moment. Sign convention is, okay. Sign convention is quite important. Actually, when you do a cut and introduce unknown internal loadings, in this case, 3 unknowns, right? Usually, you have no idea which direction those 3 internal loadings are. You have no clue. So you probably need to do a guess. So when you do when you do an initial guess, you have to probably need to go through the standard guess. It's called sign convention.
Okay, so it's the same with trusses, basically, just to switch the direction after if I get a minus.
So it's important. Okay. So suppose if you do an initial guess based on this sign convention. In other words, I have no clue which direction of the moment or normal force or shear force. I have no idea. So I'm going to assume, okay, this is the direction of normal force. This is the direction of shear. This is the direction of bending. Although I have no clue. This is just my guess. But it's called sign convention. And then suppose if you get the negative value after you do summation of forces and moments, you determine, hey, wait a minute, NC is a negative value. Oh, what do you mean by that? Well, that means NC is opposite direction.
Yeah.
Yeah. So I appreciate that, because sign convention actually becomes super important. In other words, everybody need to follow sign convention if you want to draw a diagram. So diagram, as you try to construct the diagram, you have to follow through the sign convention. Let's just remember. So I appreciate your question. This is a very important subject. So I'm just for a moment, try to follow the sign convention. Okay. So if you cut this member, exposing sort of right-hand side of the member, right? Right-hand side of the member is being exposed. That means this is a sign convention. I have no clue the actual direction, but sign convention-wise, I'm going to set NC goes to the right. This means this is tensile. Tensile is positive. So if you get the negative sign, hey, this is compressive force kind of thing. So shear force going down is positive. So shear force may be going up. If so, you get negative sign. And then moment bending moment this way is positive. If you get the negative value, you're actually having this kind of bending moment. So that's what I'm doing here. So that's what I'm doing here, okay? Right here. So this is sign convention based unknown directions. So you may end up getting negative value. Don't worry about it. That means the direction is opposite, okay? All right. I appreciate that once again. So let's just apply summation of the force in x direction set equal to 0. Okay. So this actually gives you, ooh, wait a minute. NC is the only force in x direction. Oh, that means NC 0. Okay. No normal force internally developed for this beam. It's kind of typical because the beam's purpose is to support the perpendicular force as well as moments, right? So it's kind of common to have a moment doesn't have any normal internal loading developed inside. Sure. And next thing is summation of the moment. You can take the moment at any location. Let's just take it at C, right here. Location C. If I take the location C, it is very, very useful because 8 kip going through location C, it doesn't contribute any moment. Shear force BC doesn't create any moment at location C. Normal force doesn't create any moment. So what's left? 7 kip create the negative moment. That should counteract with MC, internal loading, right? So if you do such a thing, summation of the moment taken at location C set equal to 0, you can say moment internally developed at location C MC minus 7 kip force multiplied by, this is 8 feet, is equal to 0. This is going to give you MC, which is 56 kip foot. This is the internal bending moment developed inside of this beam. Okay. Interesting. This is internal bending moment developed inside of this beam. Next is, of course, summation of the force in y direction. Once again, set equal to 0. So this actually gives you 7 kip going up, positive, 8 kip, negative, BC is again negative, is equal to 0. Interestingly, this is going to give you BC negative, negative 1 kip. So important discovery here is direction of BC is actually up. Okay, good. This is what's happening at point C. Internally, okay, at the point C, there is no normal internal loading is developed. However, at the point C, internally speaking, you have a bending moment, 56 kip foot is developed. And shear force, negative 1 kip, which is direction opposite, is developed. Okay. What does that mean? Well, do you think these values are uniform throughout everywhere in the beam? Those two. Or do you think those two will change throughout the beam?
They will change.
They will change, yes. So that means your desire is, okay, so what kind of change do you have? Well, we can draw a diagram. Then look at, okay, so your next question is, where is the critical location of this beam where you experience maximum bending loading? That's where the beam starts to collapse, right? That's a critical point internally. Well, you are interested, you can draw a diagram to find out, okay, so this is the maximum internal bending moment developed right here at this point. My goodness, if this beam is breaking down, this is the point, because this is where all the bending moment concentrates in the maximum body. So what kind of material, what kind of cross section do you need to design in order to have a hoist of 2 tons? Well, we need to have a strong enough beam for that kind of thing. So that's the next step, solid mechanics, okay? So anyways, important discovery so far is, internally speaking, bending moment and shear are developed at point C. Those are internal. This is bending moment. This is internal shear load or shear force. Okay. So let's move on to point D. Okay, so point D. So once again, you're going to introduce another cut going through point D. Now, as you cut, now you cut this original beam into 3 segments. You can freely choose either this segment or that segment for free body diagram, okay? I'm going to probably choose this one. But alternatively, of course, you can choose this one to solve this problem. Anyways, okay? So let's just draw it, okay? So point D. So point D, this cut segment, you're going to draw, or alternatively, sorry, let's just for a moment, let's just forget I just cut it through. So if you introduce a virtual cut here, you can actually choose this entire segment without cut. Completely ignore this point C. This entire segment without cut, or this segment. Okay. Then I actually use this entire thing. Okay. Okay, so point D is, okay. So you have a variety of options. You can choose this segment, or this whole segment. 3 options. I'm going to choose this whole thing. Okay. Okay, now, so point D now looks like this. So once again, this is reaction force, AY, 7 kip. And don't forget, externally applied loading, 8 kip. Once again, at the location C. Now, location C is not cut this time. Location C is here. And this is, let's call this location D. You cut through D. And then obviously, once again, you're going to introduce, based on the sign convention, this is shear force, BD. Normal force, ND. Internal bending moment, MD. So now this is just the FYI, but suppose if you choose a different segment, okay? Suppose if you choose this segment, this is once again D. It's just the other part of this entire beam. And obviously this is BY. BY is, do we know BY? BY is 1 kip, isn't it? Okay, 1 kip. And then obviously externally applied moment, couple moment. This is 40 kip-foot. Okay. That's it, right? I guess. Yeah. Okay. So in this case, let's be careful. You are going to introduce based on the sign convention. This is the assumed original direction of BD. This is the assumed original direction of ND. And this is internal moment MD. So important thing, suppose if you assemble this all member at the location D, those internal loading all cancel each other because it's equal and opposite. That's quite important, okay? So you can choose either this body or that body, applying, again, 3 equations of equilibrium to find out unknown internal loadings. And then you should get exact same results. Whichever the free body diagram you choose, you can get the exact same result, okay? So I'm going to, like I said, I'm going to choose this one, and then let's find out summation of the force in x direction. Set equal to 0. This is going to once again give you normal force. Normal internal loading at cross-section D is again 0. Oh, this is beam, so it's kind of natural. Naturally speaking, this beam doesn't support any actual loading because that's not the design for, of course. And then let's just apply summation of the moment. I'm going to apply summation of the moment at this location D. Let's just set equal to 0. So this is going to give you MD, which is positive direction. And this 7 kip create negative moment. From here to here is 16 feet. 8 kip create positive moment. Distance from C to D is, I believe, 8 feet. Let's just set equal to 0. This is going to give you MD, internal loading, 48 kip-foot. And one more equation, summation of the force in y direction, set equal to 0. This is going to be 7 kip in positive direction, 8 kip in negative direction. BD, again negative, set equal to 0. This is going to give you BD. Interestingly, this is minus. So that means the direction of the BD is actually opposite direction. Okay. So interestingly, moment changes from location C to location D. So internal bending moment is higher at location C than location D. And then shear seems to be, well, the shear, internal shear doesn't change between C and D. So that means shear being constant? Looks like. The moment changes. So I guess your interest next is what kind of variation can we expect for internal bending moment, internal shear force? Because that's going to be quite important to design a beam. Okay. Any questions so far? So this actually solved this problem, but again, the solution of this problem gives you another interesting question. Do you have any question here? Okay so far? Please react if it's okay. I hope you feel comfortable understanding what we are doing here so far. Okay, good. All right, so let's move on. So this is a homework assignment. You're going to do the similar thing. Determine the internal normal force, shear force, and moment at point C. So obviously this one, first of all, you're going to take the whole free body diagram, determine the support reaction force AXAY and support reaction force BY, and then you're going to introduce virtual cut, you can either choose this segment or that segment, applying summation of force in two directions and moment, three equations of equilibrium to understand three unknowns: internal normal force, shear force, and then bending moment. You can do this, okay? Let's take a look at another example. Example 392, determine the internal normal force, shear force, and the moment at point C and D. Now, this is not the beam. This is a frame, okay? So, how can I handle such a thing? We can do it. So first of all, the entire free body diagram. So this is a pin support. You have two unknowns. This is not the pin. This is a pin with a roller. So you have only one support reaction. This is the same as this. Do you remember this? This is basically same. Okay. So I'm going to draw entire free body diagram first of all. Okay. So it's challenging to draw a straight line on digital device. All right. So this is a pin A. Okay. So this is B. So pin A introduced two unknowns. You can actually do this, but yeah, okay. Well, you can actually do this, and then all right. So it's the same thing. This is FA. FA can be broken down into two forces, which is AY, AX. Forget about it. I don't want to do that. Okay, sorry about that. Can I undo? Sorry. How can I undo? Maybe I can't. Okay, once again, sorry about that. I changed my mind. Okay. So once again, this is the member. And this is the pin. Rather than doing actual force and then break down two components, I'm going to do an orthodox style. So this is pin. So you have two unknowns, AY, AX. This is probably much easier. Okay, so this is very traditional orthodox, two unknowns, AX, AY for the pin. And distributed loading here. So this much distributed loading, 2 kilonewtons per meter. So I'm going to probably take the resultant of it. So if you take a resultant of this distributed loading, obviously you can determine resultant force. which is the 2 kilonewton times 3 plus 2, 3, then 6 meter, 2 times 6. This is 12 kilonewton. Resultant force acting right here, 3 meter, which is location D. So let's say this is location A. Location C is only 2 meters away. It looks like, geometrically speaking, this is 45 degrees of an angle. And right here is location D. And then you have another support reaction right here, By. Okay, so I think this is a free body diagram. And first thing is you want to find out those 3 unknown support reactions. Okay, so one of them is easy, summation of the force in x direction set equal to 0. Let's say this is a positive x direction. This actually gives you ax is 0. So that means, hey, this is 0. Okay, and let's take the summation of the moment. Let's say this is the positive moment direction. Let's take it at location A. Let's just set equal to 0. This is going to create By with a distance measured from here to here. Oh, what is that distance? Well, anyways, so By create positive moment. So By times distance from here to here is 6 meter. Plus distance from here to here is, what's this distance? Anybody? This distance.
6 cosine 45.
6 cosine 45. Thank you. Appreciate that. So 6, this is the 6. This is 6 plus 6 cosine 45 is the moment arm. This is going to create a positive moment around location A. That's right. And then this 12 kilonewton is going to create negative moment. 12 times, this case is 3 plus 6 cosine 45. We are going to set equal to 0. Okay. This is going to give you By. By is 8.485 kilonewton right here. And then if you take the summation of the force in y direction, set equal to 0, this is going to give you a y that is positive y direction, and then we know By is positive 8.485 kilonewton. That's By. 12 kilonewton negative. Set equal to 0. This is going to provide Ay, in which 3.515 kilonewton looks like. So now we got support reaction. Okay. Now the question is point C. Okay, so let's just find out point C. So obviously you're going to introduce your cut going through point C. Cut. Then you can either choose this segment or the entire rest of the segment as a free body diagram. I'm going to choose probably this one because it looks much easier. And then you're also going to cut through point D. Then you're going to introduce 3 different choices. You can choose this segment as a free body diagram, or you can choose this whole segment as a free body diagram, or you can choose the other element as a free body diagram. I'm going to choose this element Okay, but you have three choices. So let's just take a look at point C. Okay. So point C, of course, you're going to choose. I'm going to choose this. You can, of course, choose this one if you want to. Point C is this. So this is C. And then right here, we basically found yeah, okay. We basically found AY. AY is 3 point, okay. Okay, so this is AY, 3.515 kilonewton. Now, we kind of add a little bit more about the geometry information in which if you do this, this is 45 degrees. Okay. And three unknowns introducing here. Shear force, BC, normal force, NC, internal bending moment, MC. Three unknowns introduced. So we are going to find out those three unknowns. So first of all, let's just do summation of the force in x direction. Let's just set this is the x direction, okay? Along the axis of this member is the x direction. Let's just set for that. Summation of the force in x direction is set equal to 0. This is going to make things, I hope, easier. So this 3.515 kilonewtons component in this direction is basically sine 45, isn't it? So this is negative 3.1515 sine 45 degrees. It's a negative direction of x plus NC is equal to 0. This is going to give you NC is 2.485 kilonewton. All right. Next is the summation of the force. In y direction, let's say summation of the force y direction. Y direction is, again, perpendicular direction to the axis of this cut member. If you do such a thing, now this component of this 3.515 kilonewton is basically cosine of 45. So this is, and it's positive direction. Okay, that's right. So this is positive 3.515 cosine 45 degrees minus BC is equal to 0. From here, you can get BC, in which 2.485 kilonewton. Same value of normal force. Okay. And then, if you take summation of the moment, let's say this is a positive direction of moment taken at location C. Let's just set equal to 0. Right here is location C. If you do that, obviously MC is a positive value. And negative 3.51. What am I doing? Okay, sorry. Moment. What moment? Oh, this 3.515 kilonewton create the moment. So you can either doing either way is fine, but 3.515 kilonewton, you figure out the distance from this force to the location C. That's one way of doing that. Or you can find the forces component, this force multiplied by this distance. Either way is fine. It's actually same meaning, but so I'm going to do, okay, I'm going to do this 3.515 kilonewton, 3.515 kilonewton times, I'm going to find out the distance here. This distance is 2 times cosine 45. In other words, that's 2 meters, right? This is 2 meters. This is 2 times cosine 45 meters. Okay. So what I'm going to do is, this is going to create the negative moment. So minus 3.515 kilonewton times 2 times cosine 45 meter. Let's just set equal to 0. This is going to give you MC. So this MC is 4.97 kilonewton meter. Okay. Okay, so far. Oh, I'm kind of getting tired now, and then running out of space too. But let's just move on to point D. My goodness. Okay, point D. Hopefully this is easier. So you're going to cut through point D. You can choose either this whole thing, or this cut segment, or this segment. I'm going to choose this one. It seems easiest, so I'm going to do that. So point D, if you draw a free body diagram, okay. Okay, so this is Py, yeah? So this is D. D is right here. This is B, okay. And By, we found it, right? Yeah, okay. So By is support reaction, we already know. By is 8.485 kilonewton. And don't forget the distributed loading. So distributed loading, which is 2 kilonewton per meter. Now you cut through D, so this is 3 meters length. So you're going to recalculate resultant force over the length of 3 meters of this distributed loading. Okay, because this is only 3 meters, so this is 2 times 3, 6 kilonewton. 6 kilonewton resultant force is acting at 1.5 meters measured from location B or D, either way. And you're going to introduce, once again, this is left-hand side cut. You're going to follow through the sign convention. Okay, so this is BD going up. This is ND going to the left. This is MD, internal bending moment. 3 unknowns shows up. So this is completely opposite direction, right? This is right-hand side cut exposure. This is left-hand side cut exposure. Be careful about sign convention, okay? This is going to be important when you draw shear moment diagram later. Okay, so this is it, right? Okay, so I'm going to apply once again 3 equations. Now this is the x direction. Summation of the force in x direction set equal to 0. This is going to basically give you ND0. No normal force going through point D. Well, this is typical result for beam anyways, because this portion is a beam. This portion is not. So obviously you're going to expect both normal and shear forces developed internally, but this portion is a beam. So normal force is 0. Interesting. And then summation of the force in y direction set equal to 0. This is positive direction. This is going to give you BD, positive, 6 kilonewton negative, and then 8.485 positive. Let's just set equal to 0. This is going to give you internal shear loading at point D, which is negative 2.485 kilonewton. Negative indicates, hey, direction is opposite, which is, yeah, it's okay. So actual direction of shear is the other way. That's fine. Then if you apply sum of the moment at location D, set equal to 0, this is going to give you, obviously, moment is negative, isn't it? Okay, negative MD. Minus 6 times 1.5 meter, okay, plus moment 8.485 times moment 3 meters. Let's just set equal to 0. This is going to give you internal bending moment developed at D, 16.455 kilonewton meter. Okay. Do you have any question? Yeah, it's quite a bit of a competition to figure out everything. So suppose, every time when you introduce your cut here, cut there, cut here, try to find out internal shear and moment, do you think you want to do such a thing? But that's essentially you need to be doing if you're trying to develop a diagram of a shear and bending moment, okay? So next page is a homework. This is a beam. So the only things you will be interested will be shear force and bending moment internally developed, not the normal force. But let's determine the internal normal force, shear force, and moment at point C of the beam, right in the center. Now, question here is, do you think location C is a critical location where internal shear and internal moment will be maximum? Do you think so?
I would say no.
You would say no? Probably.
Because
Only
like
one.
the different pressures, is that why?
This is a distributed loading, keep increasing and increasing and increasing. This is going to actually affect on the shear, big time. Okay. And then this is probably not the maximum point of the shear. So I think as you design your beam, you have to design based on where is the critical location of it. So you need to have a structure which is strong enough to support that critical moment, critical internal shear. So that's the design point, which is going to come up in solid mechanics. Okay. So, but this is your startup process at statics to find out internal loading. Okay. Another homework. Ooh. Determine the distance A between the supports in terms of the shaft length L. so that the bending moment in this symmetric shaft is 0 at the shaft center. Oh, okay. 0 moment right in the center. Okay. The intensity of the distributed load at the center of the shaft is W0. This is a linearly changing distributed loading. This is 0. This is maximum value W0 in the center. Those supports the general bearings. Do you understand general bearings? This is a smooth bearing, so this shaft is kind of free to move in this direction. So there's no way you can support normal force in this way. That means normal force is 0. You can never support such a thing. This is purely shear and internal moment type of internal loading. Okay, so obviously, how much support reactions do you have here? And how much support reactions do you have here? Anybody? General bearing actually can support the moment. Okay, in other words, this thing, if it's supported like this, you cannot rotate, but you can smoothly move around, and you cannot translate in y direction. So you have y direction support reaction, and also moment reaction also happens here. Okay. All right. So I hope you can handle. Let me just find out if I can give you a sneak peek of a solution I did. 393. Okay, so this is what I did. Okay, so first of all, support reactions, those two general bearings. Okay, so let's assume general bearings can only have y direction support reaction. Did I say it's going to support the moment? I hope I thought so, because this is general bearing. You cannot rotate. But anyways, for a moment, let's just ignore that. It's free to move this way, but you cannot move in y direction. So it's support reaction here and here. This is symmetric. So half of the vertical loading is supported here. Half of the vertical loading is supported here. Those are support reactions. Then next is you're going to cut through here, pick up either left or right cut segment. Let's call that point O. Introduce internal shear moment, normal force. Of course, normal force is 0. Is it? Yeah. And then what is the condition to make a moment 0? Then I found A is 1/3 of L. Okay. So it's just a sneak preview of how you do this homework assignment. Okay. So now let's just step into how to construct the diagram of internal two things, shear and moment diagrams. So now we shift our focus on the application of the beams. Now, as you saw, some of the example problems, beams are the typical structure, and then it is designed to take either perpendicular loading or moments. So this is the typical beam, okay? So this is pinned, supported, and roller at the other end. So introduce 3 support unknown reactions. And then you can apply a variety of things for this kind of thing. This is a beam. So this is a beam. You can apply forces, like this is called point force, okay? So you can apply point forces at any location on this beam, okay? So this is a concentrated force. And of course, you can apply distributed loading of any type. You can apply uniform distributed loading. You can apply linearly changing or non-linearly changing distributed loading for the beam. Or you can apply a moment. This is called point moments. You can apply concentrated couple moment just about any location along the beam. Okay, so you can apply a variety of loadings for the beam. So this is just a general sketch of what kind of loading you can expect for the beam. Now, one thing you can tell about the beam is normal force is 0. It's not designed for it. The beam is not going to carry normal force. You don't have to. All the loading is essentially either perpendicular direction or moment, internally bending. So if you design and build a beam, which is a common structure, this beam is under either this kind of loading or this kind of loading, trying to bend it or trying to push it at certain location, or you put something on top of it, distributed loading. Okay, so 3 different kinds. So that's what I'm talking about here. The design of beams requires a detailed knowledge, of course, detailed knowledge of the variation of 2 things: internal shear force, which is B, and internal bending moment, which is M. So you need to have a detailed knowledge. In other words, how internal shear and moment distributes from this point to this point along the direction of X. Okay, how much shear do you develop here? Is it going to increase or decrease or stay constant? How much internal bending moments develop here? Is it going to increase or decrease or stay constant throughout the axis of this beam? So you have to basically take a look inside by introducing virtual cut at any arbitrary location X. Okay, so we are going to actually plot the distribution of internal shear and moment. This is called internal shear moment diagrams. Shear and moment diagrams. Okay, this is a classic technique you need to have before you start taking solid mechanics. At the very beginning of solid mechanics, the professor will probably give you a test if you can construct the proper diagram or you have no clue how to do it. Anyway, so it's very, very important for you to master how to draw proper diagram. Okay, it's quite important. So when you start plotting such a thing, shear and moment diagrams, you have to introduce sign convention. This is very important. I already mentioned a little bit, but if you introduce virtual cut to your right-hand side of your beam structure, this is the positive direction of shear. This is the positive direction of shear on your left-hand side cut. That's what I've been doing for the previous examples. I try to follow the sign convention. And also, this is a direction of positive moment. In your right-hand side cut, this is a positive moment direction. Left-hand side cut, this is a positive moment direction. If the shear moment is applied at the end, okay, again, follow the same thing. Left-hand side is positive, right-hand side is negative. This is negative, this is positive. Right-hand side going down is positive. Left-hand side of the moment, this way is positive. Right-hand side of the moment, this is positive. So always bending moment trying to bend this way is a positive. Okay. So now let's just take a look at more details here. So this is a general situation of beam under variety of loading. Okay, it could be under the point loading, point moment, or distributed loading. So let's just take a look at the distributed loading. So at the location X, you're going to cut off small tiny chunk of material right here. Okay, so now you expose on your left and right hand side the shear and the moment internally developed. Okay, this is the delta X. So this thing is, due to this distributed loading, you're going to develop resultant. This is resultant, okay? Which is distributed loading, this is a function of x multiplied by delta x, right? So this is the resultant, the magnitude. So let's just apply summation of the force in y direction for that situation. You have a b positive. You have b plus delta b, right-hand side, which is negative. This is resultant force wx times delta x, which is negative. Yeah, that's right. All of them set equal to 0. Then interestingly, b and b cancels. You're going to get this equation. Okay. Let's do the same thing. Let's sum of the moment. Let's set, this is a point O. Let's sum of the moment at the point O set equal to 0. Then let's just introduce small tiny distance k times delta x right here. This is a small tiny gap, k times delta x. So this k times delta x times this shear force and that shear force create the moment at point O. Both included. And then moment and m plus delta m moment, right hand side and left hand side included. Now interestingly, you can cancel m and then this k is very, very, very small. Let's just ignore a whole shebang. Then you come up with delta m is approximately equal to b delta x. Important. So you got two important equations. This equation and that equation. Okay. Now let's take the delta x goes very, 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 very small. It's going to be taking the limit of delta x being 0, approaching to 0. Those two equations will give you differential equations. This is the differential equations relating the shear, internal shear to the distributed loading. This is the equation relating internal bending moment related to the external shear. Okay. So once you establish the shear diagram, using that shear, you can establish moment diagram. That's how you go. Okay. And then, of course, you can integrate these two differential equations to find out this is the change of shear internally is going to be found by negative of integrating distributed loading. This negative is because the direction of distributed loading is negative y direction. That's why. So this is the change of moment, internal moment can be found by integrating the shear distribution. Okay, so it's kind of hard to understand by looking at equations, but from now on, you need to be developing the engineering second nature. By looking at equation, you can tell what the equation really means physically. So that's your first step to understand, okay, those are the equations given. Can you use those equations to develop internal shear and moment diagrams? Yes, you should be. Okay. So let's just understand what does this equation really mean. Okay, 5 more minutes. Okay. Also, another way of look at, suppose if you look at this single point of moment applied at right here, location x. Let's just chunk out delta x at the location x, pick it up, free body diagram just like this. Okay. Let's just do the summation of force in y direction. You are going to get change of shear is equal to the force. What does that mean? Whenever you apply the point force at any location along the beam's axis, you're going to change the internal shear with the same amount in the negative direction. Okay. Also, another way of looking at it, you're going to take a look at moment. moment is applied here. So let's just take location X, and let's just chunk out small tiny segment delta X, and pick up this segment as a free body diagram. This thing is, and let's just take a look at it. If you take a moment applied at point O right here, the result is delta M is equal to M0, which is applied moment. This is a point moment. Applied at certain location. If you apply a moment, you're going to have internal moment change happens with the same amount. Okay. This is a point force. If you apply the point force, you are going to change the internal shear with the same amount in negative direction. Okay. Point force, point moment. And don't forget, this is the distributed loading. W. W as a function of X. So next class, as you come back on Wednesday tomorrow, we are going to go over this summary table. And then you really need to kind of look at this table and start thinking about what the hell does that mean? Dr. H was talking about, okay, suppose if you apply point force, you have a change of shear. Ah, okay, looks like it. Suppose if you apply the point moment, you have a change in moment. Okay, so we are going to take a look at more as you come back tomorrow. Okay, let's stop here today. Any question? Have a good day and see you back tomorrow.
Thank you, Professor.
Thank you.